Okay, so we have a reaction here, 1-iota-3-methylbutane, and we're trying to figure out the product. Okay, um, so first of all, we got to figure out what this thing looks like. Well, that's what it looks like, but... Okay, 1-iota-3-methylbutane. Okay, so when it comes to elimination reactions and substitution reactions, I consider all of these reactions with the same strategy. So up here, I have some stuff written. Actually, what was I doing? I'm tripping. Okay. I just didn't want to have it clog up the space. Okay, so this is what I do. Okay, first when I do these, I look at the alkyl halide. Okay, now there's a chart that I have here that helps determine this, almost everything, but let's work without the chart. Okay, it will for now. Okay, so we have a primary alkyl halide, all right, point A, okay, and it's a good leaving group, all right. Then I want to look at my nucleophile base, okay, and I see we have sodium hydride, okay. Off rip, I know that in solution, this is just going to be hydride, just floating around, okay. There's a few things that I do know about hydride is that it's not a very good nucleophile, okay. One of the reasons why it's not a very good nucleophile is because it has some priorities, okay. Hydrogen in nature is a pair of two as a gas, okay. So because it comes in nature as a pair of two, if it doesn't have two, you could say it's fairly unhappy, okay. So if it's unhappy, it wants a partner. So it prioritizes getting a partner over attacking something. A hydride's just not going to want to attack. Okay, so hydride's actually going to be a good base. Okay, and we can go down to our chart and check this out, right? Weak nucleophile, strong base. Okay, as we can see here, and we see hydrides among the list. Okay, so that confirms we have a weak nucleophile, strong base. Okay, off rip. Because of that, or because our nucleophile is weak, well, actually, because our base is strong, we can just say elimination's gonna go down. I hope I'm spelling that right. Okay, so if you look, every time, well, not every time there's a strong base, but oh yeah, okay. So here we have a strong base here, strong base here, strong base here, strong base here, here, and here. Okay, so only one time is a substitution reaction gonna happen with a strong base, because in reality, that strong base it's gonna pull a hydrogen before it does anything else. Okay, so we have a strong base. Where that means for me elimination most of the time. All right, I'm considering that other option. Okay, and as you guys do the homework and practice, if you just use this chart, you can easily identify the outliers. Okay, but there's patterns to this. Okay, so I see strong base, I'm thinking elimination. Okay, primary alkyl group. All right, and then I consider the temperature when I do all these reactions, because if it's hot, you're gonna force elimination. If it's cold, you force substitution. Room temperature is a toss-up, okay? But elimination, you can, like I said, you can jump to considering the other options, the few other options, if it's a strong base and if it's hot, right? If you see this little triangle, go to elimination, okay? And then cold, substitution. All right, that's just how you can do those reactions. Okay, so it's at room temperature, so we we can't just make a decision based on temperature. But what we can do is we can start working on this problem. Now we know are the players, right? We can figure out what's going down. Okay, so we're gonna go to this structure over here, right? So we know hydride is gonna wanna pull a hydrogen. It's a good base. So we know elimination is gonna happen. Okay, but how does elimination work? Well, this is how it works. When you think elimination, you think these two terms, alpha carbon and beta carbon. Okay? The alpha carbon is the carbon that is bearing the leaving group. The beta carbon is a carbon that's connected to the alpha carbon. Okay? Now, another important piece about the beta carbon is that on the beta carbon, you have beta hydrogens. These beta hydrogens are the hydrogens that are going to get pulled off in an elimination reaction, E1 or E2. Okay, so in an elimination reaction, E1 or E2, you go to the beta carbons, which are the carbons connected to the alpha carbon. And the alpha carbon is the one that has a leaving group. You go to those beta carbons, however many there are, then you look at those beta hydrogens, and those are the ones you'll pull off, right, in order to kick off the leaving group, right? Okay, so another important thing, well, actually, I'll get there when I get there. Okay, so we see a hydride that's going to pull off one of these hydrogens right over here, right? Now, in this case, it doesn't matter which one, because it's all going to, its bond line, it's going to, this bond is going to come down here to a double bond, but if it's, so because I know the answer, this is going to be an E2 reaction. Yeah. Sorry. Okay. I blanked right there. E2. So if this is E2, right? And it's E2 because, let's go, we have a weak nucleophile, strong base, and a primary alkyl halide. Okay, so we have a primary alkyl halide, weak nucleophile, strong base. That's E2. Okay. So E2. E2 is a little special, right? E2 reactions require the beta hydrogen to be anti-coplanar to the leaving group. I'm not going to get into the weeds about anti-coplanar, but basically it has to be trans to the leaving group. Okay, so if the leaving group is dashed, the beta hydrogen or hydrogens that can get pulled off have to be wedged for E2 reactions. If the leaving group is wedged, the beta hydrogens that can be pulled off have to be dashed. All right? Now, this is going to affect the product that you make because sometimes you might have two beta carbons, but maybe only one of those beta carbons has a hydrogen you can pull off because the other one isn't anti-coplanar, aka trans, to the leaving group. Right? And you see that with rings and chairs and stuff like that. Okay, but consider that. Now, this doesn't matter here, like I said before, simply because we're not looking at stereochemistry with this specific one. But stereochemistry again plays a role because that is just how E2 works. Okay, so what happens is this hydride comes in, and pulls this hydrogen to itself, right? Then this bond breaks. I'm just gonna do like a little, almost like a little transition state thingy. That bond breaks, and because the hydrogen pulled another hydrogen to itself, and the bond that was formed breaks, and the bond that was there breaks, this new bond forms. And when this new bond forms, this bond breaks. Okay, and those electrons go to the iodine. All right. Hold on, sorry. Oh my gosh. Okay. Then our product would be this, right? We don't add that extra because these electrons are being shared, right? So they're going to stay, they're going to go to the iodine, okay? So that's our product based on the E2 reaction, okay? E1 and E2 both pull hydrogens to make double bonds, right? So that's our product. Now we just got to look at our answer choices and see which one it is. And we see that it's C, okay? So again, consider the alkyl halide, the nucleophile slash base. Again, this was NaH. The temperature, and then with all those factors, just think about what could happen. I like to attempt to think about what could happen and what's probably gonna go down. Then when I need an extra boost, if I can't figure it out, I'll go to the chart. And then once I find it, I'll reason my way to figure out, okay, why is it E2? Like, why is it SN2? Why is it SN1? Instead of just looking at it and doing it. All right. And so once you consider those factors, you take in the next level into play. Once you figure out the game plan, right? Once you get to the point where you've narrowed it down to the type of reaction, then you perform the reaction, but you got to be aware of the certain parameters, right? Like, for example, E2. E2 it needs that anticoplanar. Okay, that's specific to E2. And so, but once you figure that out, then all you got to do is just find the answer. And so that's E2 reactions. Oh, and also, again, elimination is when it's warm or hot, actually. Substitution when it's cold. And then, like we said before, if you have a strong base, you're more likely to have an elimination reaction. Again, you don't have to have one, right? Like we said here, with this one, I just want to zoom in so you see it. Strong nucleophile, strong base. This is going to be an SN2. But again, this is the outlier among the ones circled, okay? So that's how I break down these. Again, this is an E2 reaction.